All right, so questions. I'm hoping to talk about modularization and what all that means, and calling functions and passing things to functions. And I want to talk about ODP 451, and I want to talk about more Linux. So, questions before we start.
Did yesterday's class get recorded?
Should have been. Is it not up there?
I didn't see it yesterday, but that's okay. I'll check.
It's always possible that I messed up. Did anybody see yesterday's videos?
I saw A, but I didn't see B.
Oh, interesting.
I thought it was out of order.
Oh, is it out of order?
I think it was just out of order.
Oh, okay.
That's very possible. If you don't find it, let me know and I'll undelete it and upload it. All right, other questions? So let me talk about ODP 451. So this is an emergency ODP because somebody actually requested an ODP using fgets, and that's an excellent idea. So so this is an fgets assignment, and you're writing a function called input, and it returns nothing, so it's declared to be void, and it has one argument, which is a character array, a char star arg. And what your function does is it calls fgets to read one line of input from standard in, and it saves the input into this variable arg, and then it chops off the last character. Okay, which was what we were doing yesterday when we said variable bracket string length variable -1 equal to null, chopping off the last character. So it doesn't actually get a value in arg when it's called. You read a value using fgets. Okay. Save it into arg, and then chop off the last character, and then just return. So you can write your fgets as just fgets. You make your first variable arg, and I comment in there. You can assume that that arg is at least 120 characters in capacity, so you can set this to 120. And then your third argument is always going to be standard in. So that's precisely your fgets call that you want to use inside your input function. And then go ahead, chop off the last character from arg, and just return. And the main program, which is calling this, right, should pass the address of a character array. And the function should wait for the user to type something, hit enter, and when the function returns, that character array should now be populated with whatever the user typed in without the new line on the end. So test your function, link it with the test bed as follows, and then assess it in the usual way. And you should be good to go. So questions about that? All right. Don't try to run your main program without, don't try to run this main program, right? This is only for assessing. If you try to run it, it'll actually say, use this with the assess utility. It's getting sneaky. All right, so that's ODP 451. So let's talk about modularization. So the whole idea of modularization, I don't even know if that's technically a correct term, but it's the term I use. Basically taking a large program that you're developing and breaking it into smaller pieces, which we can think of as modules, and putting these smaller pieces together to make some larger function. So let's just look at PA2. And you don't have to do this. Don't delete PA2 and start over because I'm doing something weird up here, okay? This is purely an example. Let's look at our stick program. And let's think about the basic functions that it performs. So what does the main program do? You know, it does some sort of welcome. So, you know, this is a stick picking game. You're going to lose. Thank you. And so on and so forth. or maybe not. Decide number of sticks to play with. And actually, let me clarify this before we go any further, because there's been some confusion about this. So there's different ways you can run the stick program. If you say stick 45, play the game with 45 sticks. Okay? That's one correct usage. If you just say stick, it should say how many sticks do you want to play with, and you type in some number, play the game with 25 sticks. Okay? Those are the two correct ways that you can use a stick program. The following are all incorrect. Yes?
I was going to say, if they don't put in like an integer, and you said that you wanted us to quit if there was any errors, we wouldn't prompt them then. Or if they put in like I instead of an integer, for the command line.
Print an error and exit.
Print error.
Yeah. So let's spec those out. So these are good, and these are all bad. So stick haha, stick -10, stick 20 haha, thanks, stick 20 space haha, stick 20.0, right? These are all errors. Or if they just say stick and the program asks how many, and they type in haha, or nothing, or -10, or 20x, or 2.5, or 2.0, or 12.0. Those are all errors, right? So any of those conditions, print an error message, exit.
Do we still have the parameter that it has to be greater than 10?
And it's got to be greater than 10, yeah. So stick 5, that's an error.
Would you ask again, or just
Exit. Print a message, get out of there. So any error, just tell them they're a fool and return. All right, so clear on that? Okay. So back to modularization. Your main program, it has to decide how many sticks to play with, right? Or if it decides you're making an illegal request, it's going to exit. Okay, if it knows how many sticks to play with, what does it want to do? Basically, ask the user how many to take, subtract from the pile, print the pile, decide how many the CPU takes, subtract from the pile, and print the pile. And do that in a big loop forever. And while you're in here, check for a winner. Check for game over. All right, so this is, I don't know, 50, 100, 400 lines of code, depending on how you write it. It's a bunch of code. It's doing a bunch of different things, because decide the number of sticks to play with has got to check argc. If argc is bigger than 2, it's got to throw an error and exit. If it's equal to 2, it's got to do an scanf on argv bracket 1. It's got to check the return value from that. If it gets an integer, it's got to make sure it's in range. And if anything goes wrong, it's got to put in an error message and exit. Or if argc is equal to 1, it's got to prompt you for the number of sticks. call fgets, call scanf, check the return value from that. If it's an integer, make sure it's in range, print an error if anything goes wrong. It's a whole bunch of stuff, right? And that's potentially, 20, 30 lines of code. And you can put that in the top of your main program. But here's something else you could do.
Do you still want us to ask a second time if we ask them how many to take and they enter an invalid amount?
That would be an error, exit. Print an error message and exit. Okay, here's something different I could do. I could take my parse function that I wrote for Friday's ODP, maybe modify it, so that it takes the argc and argv that are given to main, right, and does what we did in that ODP, check argc, see if it says that there's a command line argument, parse it, scanf, all that kind of stuff. And maybe also have it, if argc is equal to 1, have it do this business of print out how many sticks would you like to play with. Call fgets, call scanf, do the same checking on that syntax. Do all of that. And the whole punchline of this parse function is it decides how many sticks you're going to play with, or it decides if there was an error. And I'm writing parse so that if there's any kind of error that occurs, it returns -1. Okay, if there's any error, it returns -1. So all these cases, parse returns -1. Including, if my number of sticks is less than 10 and so on and so forth. If the number of sticks is valid, it returns that number of sticks, 45 here or 25 here. So in my main program, I have one statement which says parse, I pass it argc, argv, and take the return value stored in numsticks. If numsticks is -1, something went wrong, we're done, do your return. Otherwise, what do I know? Numsticks is the number of sticks to play with. So I've taken that 20 or 30 lines of code and slammed it all into one function call and one if statement. My main program just got a lot smaller. Okay, now we need some kind of while loop. And this is not the slickest way to do it, but let's just do while 1. Well, okay, do a printf, do an fgets, do an scanf. If it's not an integer, if it's an integer that's not 1, 2, or 3, if anything goes wrong, hop into a while loop and keep asking them to enter a number 1, 2, or 3 and keep trying until they put in 1, 2, or 3. So you got a little while loop buried inside this along with some ifs, fgets, scanf, more ifs, right? Throw that into a function. Make a function called, get user move, and it returns a 1 or a 2 or a 3. And all the details of error checking and retrying and so on are buried in that. So I could just do usernum equals get usernum, and I've declared usernum to be an int somewhere. It's one function call, and it gathers up all that behavior, right? And then subtract it from the pile, so pile, numsticks equals numsticks minus usernum. And then print out the pile, right? I'll just say print pile numsticks. So numsticks equals numsticks minus usernum. So subtract the number from the pile and then print out the pile. And I've taken the whole user move and basically thrown it into 2 function calls and 1 subtract statement. So my main program is going to look a lot like my high-level pseudocode, right? And if this makes sense to me, that this is the gameplay I'm after, and that's what my main program looks like, debugging my main program is going to be really, really simple. As opposed to my main program is 77 lines of C code, and I've got to figure out, if I've got an error down here, well, what was it trying to do, and so on and so forth. So you're taking things that sort of logically belong together, and you're saying, let's just make a function to do this. Okay. And it takes some thought, right? How to do this. I want to check if the game is over. Well, I could put an if statement here saying if the number of sticks is equal to 0, print the user 1, good game, and then return, right? I could put that inside my print pile function, right? I could have this check to see if the number of sticks is 0. I could have it return a value, and I could say if print pile equals 1, game's over, return. I could make a function called subtract from pile, and have that subtract from the pile and also check to see if the pile is equal to 0. You can split it a lot of different ways. Let me show you an even more extreme way to do this. There's some extreme modularization. I can make my while loop basically have two function calls, user turn and CPU turn. And then all of this would go inside this function called user turn. And I still need a way to exit, but I could have user turn return a flag. If it returns 1, the game is still going. If it returns 0, the game is over. So now I could say if user turn equals 0, print good game, you won, return. If 0 equals CPU turn, print I won, goodbye, return. Yeah?
At some point, like, doing this level of modularization just gets more confusing, doesn't it?
It can, yes. And so it's, another one of these sort of personal balance points. Because I could make this whole thing just like, play one round as a function call. And that's probably way more modularization than I would do personally. And play one round could call user turn and CPU turn. It's possible you could break this into 10 million different functions, and now you've got a separate kind of nightmare because each function is really small, but you've got to mentally build up the chain of what's calling what, right? So there's a balance point somewhere in between, and you want to figure out where that is for you. And it's different depending on the problem. Personally, if I was coding this right now, I would probably do a function for how many sticks the user takes, do a function for print pile, do a function for deciding how many sticks the CPU takes, and then just wrap that all in a while loop inside my main, and probably make a separate function for parsing the arguments, and maybe a separate function if there's no arguments for prompting for the number of sticks.
Did we do a flowchart on this yesterday?
We flowcharted this a long time ago, but not recently.
Can we retouch it?
Yeah. So you want to do a flowchart or structure chart? Structure chart was the boxes that actually map to like while loops and stuff like that. Flowchart is arrows.
I feel like since we're doing it with functions and we're doing it in C, I feel like a flowchart would be more.
All right, let's go for a flowchart. So we might print out a welcome message. We could decide whether to say welcome before we tell them that they messed up on the number of sticks or after. I'll just print a welcome message in the beginning. argc bigger than 2. If it's bigger than 2, there's an error, and we'll just return. If argc is not bigger than 2, is it equal to 1? If it is it a valid int? If not, we'll print out an error and return. If it is a valid int, then just save the integer that you parsed into this number of sticks variable. Okay. If argc was not equal to 1, sorry, argc equal to 2. If argc is not equal to 2, then there was no command line argument given. So ask them how many sticks do you want to play with. If it's a valid int, if it's not a valid int, print out an error and return. If it is a valid int, just set your number of sticks equal to the integer that you parsed. And now we go on to the second page. So there's your startup flowchart, a startup flowchart. Print you're welcome. If argc is bigger than 2, it's an error, goodbye. If argc is exactly 2, they have a command line argument. If it's not a valid int, print an error, goodbye. If it is a valid int, save that integer in number of sticks. If argc is not bigger than 2 and it's not equal to, it must be equal to 1, so ask them how many sticks they want. If it's not a valid int, print an error and return. If it is a valid int, save that in the number of sticks. So now, numsticks is our number of sticks we're playing with. So now we're going to loop. So ask the user how many. And is it a valid entry? If it's not, print an error message. Go back and ask them again. If it is a valid number of sticks, adjust numsticks to be the number of sticks minus however many they took. Is the number of sticks equal to 0? Yes. User wins. And return. If the number of sticks is not 0, go down to the CPU turn. So this is the user turn. This is the CPU turn. So the number you want to take is the number of sticks mod 4. If that tells you should take exactly 0 sticks, take 1 stick. So take either the number of sticks mod 4, unless that is 0, in that case take exactly 1 stick. Subtract from the number of sticks, numsticks equals numsticks minus take. Numsticks equals 0, yes. CPU wins. And return. If numsticks is not equal to 0, go back up to here. Guess I could have called that 2. And then ask the user the number of sticks to take, and so on. I forgot to print the pile of sticks. Print the pile of sticks.
Okay.
Probably after you do that, yeah. BPS, print the pile of sticks. Something like that basically gets you there.
Okay.
Do we need to check to make sure that the user doesn't take a number of sticks to make the file -1 or -2? So like one stick left.
I'm not going to check for that because I didn't actually mention that in the original assignment. But if the user can make the pile negative, they can also make it 0. So I would say, you know, once they take a number of sticks, if the number of sticks in the pile is less than or equal to 0, tell the user they won. Unless you want it to be a super secret option where you like blow up the screen or something.
Steals
Yeah.
all your passwords.
Can we
Oh,
use
jeez.
enumerators for error flags?
Sure.
Okay.
Yeah. Or structures. If you want to pass back a structure and store like, you know, a value and a flag to show if it's a real value or not, stuff like that's always cool.
So I've kind of created a situation for this assignment where I am in a situation where I have like 90 lines of code.
Mm-hmm.
I was thinking about trying to, you know, create something like this where there's multiple functions and things. The issue I'm pretty much thinking about though is trying to convert all the code from one section to the other.
Mm-hmm.
So how do you copy and paste lines of code from one file to another one? So I know you can do that within one file, but I don't know if you can between.
So yeah, so here's a file 1 that's got a bunch of stuff all kind of like, so you're trying to go between 2 files or?
Yeah, so copy stuff in one file and then paste it to another.
So if you've only got to do that with a little bit, right? So you can count lines, right? So that's 6 lines. So I can do 5k to go to the top. I can say 6dd, write that, and then I can vi my second function, and I can say paste with a p, right? And save that, and then Control-Shift go back to my first one, and I can take these 12 lines and delete them, and then vi my function 3 and say paste that there with a p. But an easier way is, if you want to break it into 4 pieces, just make 4 copies of your program and then get rid of everything that you don't want. So like $delete gets rid of all of that stuff, or just bang on the DD option.
So for creating another VI file within VI, how do you do that again?
So if you're in VI, you can say :vi new file, and it'll start editing that. And if you want to go back to your first one, you can just do Control-6, and it'll take you back to your previous. So you can hop back and forth pretty easily.
All right.
Or, you know, you could say :vi in the file name to go back. But if I'm doing a bunch of things, I usually just make a bunch of copies and then just hack up each one by getting rid of stuff, because destruction's easier than creation usually. All right, other questions? So let's look at what this looks like in code. So here's an example where I've got a main program and I've modularized it into 3 functions: function 1, function 2, function 3. This has nothing to do with PA2. Don't put this into your PA2. It's just a sample. It's throwaway code. So my main program calls function 1, which is some kind of welcome message, calls function 2, which reads a number from the user and validates it, and then it calls function 3, which prints out a bunch of vertical bars, however many times I specify in the argument. And I've split it into these 3 functions. So function 1, it doesn't return anything, so it's declared to be void, and it just prints out, you know, a welcome message. Function 2 doesn't take any arguments, but it returns an int. So what's function 2 look like? Well, that's just an input loop that prompts the user to enter a number, calls fgets, calls scanf, and if scanf does not return a 1, it prompts the user again, calls fgets again. And then it does the rescanf at the top of the while. If it's not a 1, prompt the user, call fgets. Eventually, if the user puts in exactly 1 integer, scanf will return a 1, and we'll kick out of this while loop, and we'll just return the number. And then function 3 is just a for loop that whatever the argument value is n, it just prints out that many pipes and then prints out n in parentheses and returns. So that looks like a piece of the match game. And I needed to prototype my 3 functions, meaning before I call them in main, I need to specify, usually outside of main, what these functions are called, what types of arguments they take, and what values they return. So function 1 takes no arguments, returns a void. So I said void func1 paren, semicolon at the end is critical. If you don't have a semicolon, it expects you to actually write the function next. Okay, func2 takes no arguments, returns an int, so I declared it int func2 paren. Func3 takes an integer and doesn't have a return value, so it's void. So void func3 int. Now I could have said void func3 int n like I did down here, but the n would be ignored. Because the only thing I care about when I'm prototyping is what's the type of the argument. The name of the variable that I'm going to put here doesn't do anything except maybe confuse you. So this is just a type of variable, int. And then to call a function, you just type the function name. If you're supposed to pass arguments, you put those in parentheses and pass them. And if it's giving you back a return value, you can say variable equals the name of the function. It'll run that function, and whatever value returns from that function, that's the value of the function. And when I say something like I equals func2, I will be equal to whatever the value of num was right here. So you can pass things into a function, you can take a return value back. And then all of that should compile. So that's just a sample of some of the mechanics of modularizing code. So this business of modularizing is a general theme. And there's kind of 2 styles or 2 versions of this that we can think about. One is called top-down, and that's really what we're looking at here is we start with the highest level of our code, which is the main program, right? The whole thing that it's supposed to do, play this stick-picking game. And we break that into a set of smaller pieces. And we don't necessarily write those small pieces. We simply create a main program that calls them. To do that, we need to have a really clear idea in our heads what these functions do. What is func2 going to do? What is it not going to do? What's it going to take as an argument? What's it going to return? You got to have that nailed down. Okay? And then you don't have to actually write func2. You can use it in the main program as long as you really understand what it's going to do eventually. So you can finish your main program without actually writing any code. It can just be a bunch of calls to other things. But at some point you got to sit down, you got to actually write func2. And so here we're writing some C code, but I might break this into a bunch of function calls also. I might have a function call called prompt. I might have a function which says, is this a valid number? And then my while loop would just say, well, it's not a valid number, get a new number. And get a new number would prompt, it would do fgets. And is it valid would do the scanf and the ifs and so on and so forth. So that's a top-down methodology. A bottom-up methodology, we would start by writing the lowest level functions. I'm just going to write a function that lets the user type in a number and tells me whether it's a 1, 2, or a 3. And once I've got that, I'll write something called user turn that deals with the user turn and loops if they don't put in a valid number and so on. And you build your way up from the bottom to the top. And sometimes you do both. Top-down methodology is very popular right now. It works really well with object-oriented design. CSE 223, Java, it's all going to be object-oriented. And the idea of an object is it's a little chunk of code that has a whole bunch of functionality to it. It's got variables, it's got code, it's got all sorts of stuff to it. We could make an object that represents a user turn. And we could just simply use that object in our main loop. And Java comes with gazillions of objects already bundled up and ready for us to use. There's objects for putting a box on the window that has a little X in the corner and a little plus sign you can click on to maximize. And there's objects that will let us build something called a linked list, an array that has no limit to how many things it can store. and there's objects for all these things. And as Java programmers, we just kind of grab these things and put them together. They're like Tinker toys. We don't have to reinvent these building blocks. They're out there for us. We just put them together however we want. You buy a cool camera and you want to do some work with it, you get an API that goes with it. It's a bunch of Java objects that let you interact with it. If you've played with Arduino, you've done this. Right? If you want to hook a servo up to an Arduino processor, you don't have to write code to control the servo. There's code that already does that. You just say server go 25 degrees and goes to 25-degree angle. So it's a methodology we'll use in 224, we'll strongly embrace in 222, and it will be almost synonymous with what we're doing in 223 in spring, where it's all object-oriented. All right, so questions about that? This code is on the server under modularization example.c, so you can get to it from Canvas. All right, let's talk about wildcards. So we didn't talk about this yesterday, right? Okay, good. My notes are accurate. So I can say ls, and I can get a list of all the files in my current directory. All right, we know what ls does. Suppose I just want a list of all the .c files in my directory. So it turns out I can say ls *.c, and that means list any files that start with anything, followed by a dot, followed by a C, and that shows me all my source code files. I could also say ls question, 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 question. A question mark is a wildcard that matches one character. So this will say, show me all the files that have exactly 4 characters in their file name. So I get argc comp and go.c. And so if I want to see how big all my C files are, I could say ls-l star.c, and there's a long listing of all my .c files, and I can tell immediately that go3.c is my biggest file. It's 579 characters. And go.c is a tiny little file, 126. So wildcards are useful, and it turns out almost every Unix command works with wildcards. For example, I could say vi star.c, and it's now editing 4 files for me, one at a time. I'm editing fgets. If I say :n for next, now I'm editing go2, :n takes me to go3, and :n once more takes me to go.c. And if I say :n again, it'll say that's the last file. So vi works with wildcards. If I say gcc-c star.c, it compiled each of my .c files into a .o file. So GCC works with wildcards too. I can say copy star.c into this directory source, and now if I look in source, it's got copies of my 4 .c files. So CP also works with .c, with wildcards. I could say remove star.c, and now my .c files are gone. I removed all of them.
Oops.
Oops. But I can copy source/star into my current directory, and now I'm back.
Nice.
Yay. So wildcards are really, really useful. And they work apparently with almost every command in Unix. So how does that work? That seems like a lot of effort to, when you're writing a GCC program or an LS program or an RM program, to have to put in code which says if you put in an asterisk, then look in your current directory for anything that matches this pattern. Pattern matching is a hard problem in general. And there's a really, really clever trick that Unix uses to get around this. So let me take a look at this go.c program. So this is, when we were first playing with argc argv, this was some test code we used. Go is a simple main program which looks at argc and uses that to print out the value of each command line argument. Okay, so if I compile this and I say go, this is a fun day, it tells me argv0 is go, argv1 is this, is a fun day. So I can use this to see command line arguments. Okay, if I say go star.c, guess what it's going to say? arg0 is go, arg1 is fgets.c, arg2 is go.c, go3.c, go.c. Now there's nothing in my code which said if argv bracket 1 is equal to an asterisk, then look inside the current directory for anything that matches this pattern. Right? All that this program is doing is printing out the command line arguments. But when I run it and I have a wildcard, it somehow knows what to do. So here's the trick. In bash, if I type in a command and I have wildcards somewhere on the command line, before it runs the command, it evaluates the wildcard and expands it into a list of file names. So my Go program is never seeing the 4 question marks. It's never seeing the star.c. My Go program is just seeing a list of file names and it's printing out each command line argument exactly like we told it to. So if I say go/bin/star, right, that's what my Go program outputs. Why? Because it was called with 168 things on the command line. /bin/star got replaced by bash with 168 strings separated by spaces corresponding to every file in /bin that matched the pattern star, which is basically everything. So wildcards are pretty much always available to us. Now if you put things in double quotes, that suppresses the wildcard expansion. So if I say go quote star.c, it tells me you got one argument, which is star.c. In fact, if you say vi quote star.c, I'm editing a file called star.c. And if I do an ls, I've got a file called star.c. And if I try to remove it like this, I'm going to remove all my C files instead.
So then you would use quotes to do that. Disgusting.
Yeah. But guess what?
Oh, God.
No, that's good. But I get nervous about that, so I would probably, first I would say ls $.c and make sure there's only one thing, and then I would remove that. Or I'd rename it first and then remove it. Or you just be brave and just delete it. Oh, and this was the other comment on modularizing code that's already been written. So if you're going to do that, right, push everything over to GitLab first, right? And make a new directory and copy things over and start working in a new directory. I'd say leave your old code intact. Just in case, yeah. All right. So wildcards are our friend. Directories. So we know about directories, right? You can say pwd, so your current directory. ... is a shortcut for your parent directory. So if I say cd ... that'll move me into the 224 directory. And if I cd ... again, that'll move me into home nic files. If I do it again, it moves to home nic. If I do it again, it moves to home. If I do it once more, it moves me to /. That's the top level directory. If I try to move above that, it'll just leave me in / because it's the top level. You can't go above that. If you just say cd, that takes you to your login directory. That's wherever you are when you first log in. For me, it's home nic. And if you just type in a directory name without a / in the front, it takes you to this directory underneath your current directory. So if I try to go into haha, it'll say there's no such file haha or a directory in this directory. But I can go into 224 and so on. Or you can say / and put in a directory, and it'll take you to that directory, in this case /bin. And so on. The other thing you can do is push directory. So I can say push directory /home/Nick. And it changes my directory to /home/Nick, but it's remembering where I was. And when I did that push D, it showed me I'm now in tilde. Tilde means my home directory. But I was in my home directory /files224gets. And now if I want to go back to where I was, I can just say pop directory. And now I'm back where I was when I pushed. And you can do this multiple times. Right? And each time you do this, it shows you your stack. So you are currently in /, you were previously in etc., you were previously in bin, and then tilde your home directory, and you started off in this directory. And each time you pop, it takes you back one level, and it shows you what's currently on the stack. So if I try to pop from here, it'll tell me your stack's empty. It's a stack underflow. So if you've done 270, this is the stack in engineering 270. First in, last out. All right, I will talk about XXD tomorrow. One more command, fortune. So fortune will give you a daily fortune.
Thanks.
I don't know if they're all safe for work, but
Are they all the same for all of us?
no, it's randomized.
Oh, okay.
And there's also Ask Khan, which is a customized version written by a student named Khan last year, and these are related to the CS sequence. So there's 2 fortunes available. All right, so I will see you tomorrow. We'll talk about some more Unix commands. Bring questions. I have office hours tomorrow from 7 to 9:30. If you're having problems with the programming assignment, come to office hours. Okay, Tuesday, Thursday, 7 to 9:30.